Okay, so today we're going to be grasping the concept of differentiability. Differentiability. And to understand differentiability, we're going to have to look at an altered version of the derivative. So we know the definition of the derivative as a function of x is equal to the limit as delta x approaches 0 of f of x plus delta x minus f of x, all of that over delta x. You can apply this to get an altered version of the derivative. The derivative at a point. The derivative at a specific x value. And you could use this limit definition to derive this as a limit as x approaches c of f of x minus f of c over x minus c. Okay, so with this, with a limit, finding out if a function is differentiable is a lot similar to the method we use to find out if a function is continuous. Okay, you would take this limit from the left and from the right. The limit as x approaches c from the left of f of x minus f of c over x minus c is equal to the limit as x approaches c from the right of f of x minus f of c over x minus c. Or basically, we have a function over here, and this is our c value. If the slope of the function, if the slope of the function approaches the derivative of c, f prime of c, the slope of the function at c, if it approaches this value from the left and approaches the same exact value from the right, so approaches the same slope value from the left and the right, we say it's differentiable at c. Differentiable at c. And if the function is differentiable on every point, every c between an interval from a to b, then it's differentiable across the entire interval. Okay? So if it's differentiable on every point, and one more important thing to note is if it's also differentiable at a and b, that means it's differentiable on the entire interval. Okay. So what we're going to do is we're going to use this to test out and explore different ways a function can be differentiable and non-differentiable. So I'm going to rewrite our little thing over here. Limit as x approaches c of f of x minus f of c over x minus c. Okay. So what you want to do now, okay, is we're going to start testing a couple of functions. Let's start with a piecewise function. Let's call this 1. This is 3. So we have the function f of x equals 3 for x is less than 1. And negative x plus 3 is if x is greater than or equal to 1. So you could see it's clearly not continuous at 1. Okay? It's clearly not continuous at 1. So you can imagine it's not differentiable at 1. The slope of the graph of f does not exist, and we can verify that. Okay, by taking this limit from the left and from the right. So let's take it from the left. Okay, the limit from the left of f of, so I'm going to just rewrite this with the actual number. Replace c with 1 from the left of f of x minus f of 1 over x minus 1. Okay? And as you can see, if you were to evaluate this, well, f of x and the numbers left of 1 would just be 3 minus f of 1, which would be 3 minus 1 is 2, over 3 minus 1. 3 minus 1. Okay, wait a minute. So it's not, that's f of x. We're looking at x over here. My mistake. So it's 1 minus 1. We get 1 over 0. So it does not exist. So it's infinity. Okay, so does not exist. It doesn't go to a real number. Let's try to limit as x approaches 1 from the right. So we have f of x over here is negative x plus 3 minus f of 1. F of 1 we know is 2 over x minus 1. So what we're going to do is simplify all this. Negative x plus 1 over x minus 1. And if we substitute for all of this, we get 0 over 0. We get 0 over 0. Zero over 0. Okay, so in order to find the actual limit, what you can do is factor out a negative 1 from the top. So you get x minus 1 over x minus 1. Cancel, cancel, and we get negative 1. So you can see that this is not equal to this. This limit from the left doesn't even exist, much less is equal to negative 1. So it's not even differentiable. It's not differentiable at x minus 1. Not x minus, x equals 1. Okay? And we can come up with an important conclusion. If f is differentiable, then it is continuous. It has to be continuous. Because if f is not continuous, then it can't be differentiable. So if f is differentiable, it has to be continuous at a point. Okay? However, there are functions that are continuous at a point, but still not differentiable. So let's look at the absolute value function for a minute. So let's look at the absolute value function. F of x equals the absolute value of x. Okay? So you could see here, okay, that it's relatively differentiable, but there's one point that seems a little bit suspect, and that is x equals 0. So let's test the differentiability. Let's test the limit as x approaches, so that's going to write our general formula, f of c over x minus c. So we're going to test the limit as x approaches 0 from the left first. And that is the absolute value of x minus 0 over x minus 0. Or the limit as x approaches 0 from the left of the absolute value of x over x. Okay, so from the left, all the x's will be negative. So if x is negative, okay, if x is less than 0, then the absolute value of x will equal negative x. Because all of these x values will be negative. So for the absolute value to be positive, you have to take the negative of that number. So that negative of negative equals positive. So it's how the absolute value function is defined. So if we were to go to here, we were to replace this with negative x over x. And we just get the limit of a constant, which is negative 1. So it exists. Let's test the limit from the right. So we get the absolute value of x over x. Same exact thing. However, in this case, all the x values are positive. So you don't need to do anything. It's defined, the absolute value function is defined, you can define it as like a piecewise function, as negative x if x is less than 0, x if x is greater than 0, and just 0 if x equals 0. Okay, you could define it that way because the absolute value function is defined to be only positive. So if x is already positive, you don't need to do anything about it. So that just becomes a limit as x approaches 0, okay, of x over x, which cancels, and we get 1. That's the limit of a constant. However, negative 1 does not equal 1, which means it's not differentiable. So for a sharp turn or a little kink like this, it's not differentiable. And there is one more function, type of function we're going to look at. So we're going to look at the function f of x is equal to the cube root of x, or x to the 1/3, which basically looks like this. Okay. So just like the last one, it's continuous everywhere. Okay? However, we're going to first check this point since it's a little bit suspect of a point that's not differentiable. So what we're going to do is test out x equals 0. So we have the limit as x approaches c. It's always good to write the formula. F of x minus f of c over x minus c. Okay? We're going to evaluate this limit from the left and from the right. So limit as x approaches 0 from the left of f of x is x to the 1/3 minus f of 0, which is 0, over x minus 0, which is x. And now this results in the limit as x approaches 0 from the left. So from the left of x to the 1/3 over x, which equals the limit as x approaches 0 from the left. Well, x to the 1 equals x to the 3/3. And you get these little exponent laws to simplify this into x over 1 over x to the 2/3. Okay? So as you get closer and closer to 0 from the left, okay? As you get closer and closer to 0 from the left, for the negative values, okay, this will become more and more closer to 0. So you'll get negative 0.00001 as you get infinitely closer to 0. So you get a limit that does not exist. Okay? You get infinity. Infinity. So you have infinity. So you have infinity, which means it doesn't exist. This limit doesn't exist, which means the entire function is not differentiable at x equals 0. So it's not differentiable. So you have 3 options for a function not being differentiable. So A, not continuous. So A is not continuous. B, there is a sharp turn. And C, there is a vertical section. Vertical section / tangent. And if any of these are present in a function, you could say that they are not differentiable.